Let's wait for 2-3 more minutes so that people join. Hope you can see my screen and hear me clearly. If not, leave a message on chat. Okay, let's get started. Welcome to week 7 of the Operating Systems Fundamentals course, the CS100 course of the NPTEL program. I am Prashanti and I'll be handling the live session at this time every week. So, a quick recap of the live sessions. There are 3 of these. You can find details on the course page. These will be focused on problem solving, and by default all questions and interactions will be through chat because it's harder to manage multiple people simultaneously unmuting. And post the session you will be getting access to the slides and the videos. Okay, since people are still joining, I'll just wait 1 more minute on this slide. Okay, moving ahead. In case you have doubts on anything from that week's course content, something that you would like to discuss or seek clarification about, please post that also on chat. I will ask at least 2 to 3 times during this 1 hour session so that people get a chance to ask at different points. But feel free to post anytime, right? And in general, I prefer it to be a very interactive session because it helps me tailor my how I answer these questions depending on what you have confusion with or what you're very clear about, right? So the way we'll do this is we have all of these questions with multiple options. So I'll read out the question, wait 30 seconds for an answer, and then I will explain what is the answer and why it is the answer, and I'll again pause for 30 seconds to see if you have any doubts on that, right? So feel free to ask anytime you don't understand something or you need more details on some part of the explanation. So let's start with a quick sort of skim through of whatever we covered in week 7 through your lectures. So we mainly we stopped off in week 6 at what is the critical section, what is the critical section problem, and we said that every solution that is proposed for the critical section problem should satisfy all three conditions: mutual exclusion, progress, and bounded weighting. And then we started looking at some of the solutions for these problems, starting from Peterson's algorithm, which used two variables. And then we looked at some locks and the hardware support that's provided or needed for these locks. And we looked at some primitives like test and set or compare and swap. And then we moved on to mutex and semaphores. And again, we discussed things like busy waiting, we discussed spin locks, and then finally we looked at deadlocks and starvation, and we also looked at priority inversion and a solution to that. And finally, we looked at monitors and condition variables, and we moved to a few examples, a few classical examples of these critical section problems, like the producer consumer or the bounded buffer problem, the readers writers problem, and the dining philosophers problem. So most of these are all of these or most of these concepts will be tested through today's questions. So let's move on to that. So the first one is a simple question. Concurrent access to shared data may result in data insecurity, data inconsistency, data consistency, none of the above. Any guesses on the answer? I'll wait 30 seconds. Any answers to this? Doesn't matter if it's right or wrong, this is not a test, so it's okay if you get it wrong. No answers? Let's take a look at what's the right answer to this. So the answer is data inconsistency, and we saw this at the beginning of the critical section problem, right? So if two processes try to access shared data concurrently, then you might end up in a data inconsistency situation, because one of these processes might be writing and at the same time another is trying to write it, and because these high level instructions that you see are not atomic, they might get processes might get switched out or preempted because of scheduling decisions, and therefore you might have some kind of a race condition which results in the data being some uncertain value that you cannot deterministically predict, right? So this is termed as data inconsistency, and that's the right answer here. It doesn't result in data insecurity because this is shared data by design. Data consistency, no, it might result in data inconsistency. And the interesting question is it enough if we provide some kind of protection mechanism only when one of them is writing, or do you need such protections for processes which read data? That's something to think about. In the meantime, are there any doubts on this answer, or is it clear? Okay, if not, let's move on to the next question. Peterson's solution is a good algorithmic solution which works for how many concurrent processes? Your options are 2, 3, 4 and 5. If you remember Peterson's algorithm, this would be a very easy question. Any answers to this? No answers? Okay, let's look at Peterson's solution then and then answer this. So the right answer to this is two processes, and to see why, we'll take a quick recap of Peterson's algorithm. So this is a software or an algorithmic solution which holds only for two processes, and the assumption for this is that load and store instructions are atomic, as in there cannot be an interrupt while this is being executed, and that's an important assumption because without that the solution wouldn't hold. So what we do here is we have two variables, turn and a flag array. The turn indicates whose turn it is to enter the critical section, whereas flag indicates if a process is ready to enter the critical section. So as you see the algorithm here, let's take one process pi which wishes to enter the critical section. It sets the flag for itself to be true, but it sets the turn to that of the other process, and it waits while the flag of the other process is true. Why it needs to wait is because this means that the other process also is ready to enter the critical section, and it waits as long as the turn is of that of the other process. So it keeps waiting here till this condition is true, and after that, when either of these changes, for instance the other process no longer wishes to enter the critical section, it comes out of this while loop and enters the critical section, or in case the turn variable has been set by the other process to this one, even then it can enter the critical section, right? And if you think about this for a bit, you'll realize that this is by design. the way it is, it works only for two processes, right? And after its critical section, it immediately sets the flag variable as false because it is no longer wishing to enter the critical section. So is this solution clear? Or are there any doubts? I'll pause for 30 seconds. If there are no questions, let's move on. So question 3 says a minimum of how many variables are required to be shared to solve the critical section problem? 1, 3, 2 and 4. Here are your options. Any guesses on what's the answer to this? Please type out on chat. Does anyone have an answer to this? What do you think is the answer? Okay, C, 2. Great. Does anyone agree with C? Does anyone think it's something different? Let's look at the answer then, if there are no other answers. So the answer is C, 2, and the perfect example is just the question we discussed before, right? Peterson solution, where you don't have, where you have just two variables that are shared, and that solves the critical section problem. It does solve it because, as you can very clearly see here, it's not possible for both Pi and Pj to enter the critical section. This is because even if they are executing very closely separated in time, one of the variables will finally set the turn, one of the processes will finally set the turn variable. So if Pi gets to set the turn variable last, it will be j, whereas if Pj gets to set it, then it would be I. So because of that, both the processes cannot enter into the critical section at the same time. So this does guarantee that for two processes, and therefore the answer to this is 2. And something interesting, think about what would happen if you removed one of these variables. What would happen if you removed the flag variable? What would happen if you removed the turn variable? Does it at all guarantee a solution to the critical section problem? Or does it guarantee a solution while violating one of the conditions, let's say progress or bounded weight? That's an interesting thing to think about, and I think it's part of your this week's assignment. So we won't discuss that here today, but think about it. And if you're still unable to figure it out, we'll discuss it next week. Any doubts on this? If not, let's look at the next question. Since we are 20 minutes into the session, I'll remind you guys about this again. If you have any doubts on the previous week's content, the lectures that are recorded and made available, please post questions on chat and we'll take them up either right away or towards the end of the session. This live session is intended for you to get your doubts clarified, right? So don't hesitate to ask. Please post your questions on chat. But moving on. So semaphore is a dash which is used to solve the critical section problem. Special program for a system, integer variable, hardware for a system, none of the above. Okay, B, integer variable, great. Anyone else? I'll wait a little more in case anyone has other answers or the same answer. Feel free to put it on chat. Okay, if there are no other answers, the answer is integer variable, and it's a pretty straightforward question, right? And in case you don't remember what semaphores are, so semaphores are again synchronization primitives, and it's simply an integer variable that you can access via two operations, and the key assumption is that these operations are indivisible or atomic. So they were originally called P and V, and they're later on referred to as wait and signal, right? And I think you remember the whole increment and decrement that's associated with these operations. So a semaphore is simply an integer variable. It is not hardware or a special program. This much is pretty straightforward. But what I would encourage you to do is, beyond these questions, think about these things, right? Use these as hints. So for instance, when I see this option saying hardware for a system, I think about what is the hardware support that you need for some of these software abstractions or notions to work. For instance, we speak about context switching, right? What support do you need from hardware to make context switching work? Or what support do you need when a page fault happens? Similarly, here in this module, we are talking about synchronization. We speak about things like mutual exclusion, where only one process can access critical section at a time. And we look at many solutions to this at the software level, right? Like we discussed Peterson's solution just a couple of questions back. And a lot of these software solutions assume something from the hardware, and in some cases some of them require support from the hardware. For instance, we saw things like test and set, right, that the hardware provides, which is an atomic implementation. You cannot interrupt that in between. Sometimes you do need hardware support like that for these software primitives to work as expected. So that's something to think about, but the answer to this question is pretty straightforward. It is simply an integer variable. Now how this is implemented, right, underneath. So basically, if you see this recap slide, it says that this wait and signal are indivisible atomic operations. Now how are these implemented, right? Is it purely using software, or does it use a hardware primitive like test and set? That's something for you to think about in terms of this question. And there is always this notion, if you think about your earlier modules like processes and threads, we spoke about a lot of things like context switching, having multi-processing, and each of those things requires support from various levels in the stack, right from the OS to all the way down to hardware, right? That's something important to know and differentiate all the time. But if you have any doubts on this question, feel free to ask. I'll wait here for 30 seconds and then move on. Great. Let's look at the next question. Process synchronization can be done on a software level, hardware level, both software and hardware level, none of the above. What do you think is the answer to this? We were just talking about this. I didn't realize this question is coming up next. But yeah, what do you think is the answer? Do you always need hardware support for synchronization, or can it be done on a purely software basis? Does anyone have an answer to this? Do you want to take a guess? If not, okay, C. Great. Couple of people think it's C. Anyone who thinks differently? Let's look at the answer. It is C, both software and hardware level. As you remember from week 7, I'm sure, you have hardware support in the form of atomic instructions, and these are helpful in implementing locks. So you have two major types of instructions, test and set. This test memory word and set value is also referred to as TSL, which stands for test and set lock. You also have some kind of swap instruction which swaps the content of two memory words. So both of these can be used in locking, and as we've previously seen, there can be solutions that are implemented on a purely software level. Now, why would you need something to be at a hardware level? What benefits would that give you? Is many times in systems design, when you implement something at a hardware level, the cost of that might be high, as in you need to put in hardware and you need to do this for every single part that you produce, right? If you're talking about a CPU vendor needs to support this instruction in every single machine, which might be easy because it's an ISA level change. But if you need some dedicated hardware to implement that, then that is a costly thing. But why is that done? If this is something that's going to be used often enough, then the performance you get by implementing something in hardware is usually quite superior from something you implement in software, because when you do it at a hardware level, you're doing it at the lowest level possible, right? So the overheads are lesser. Whereas if you do it at a software level without having hardware support, it is still possible to do, but it usually is not as performant. It has a higher overhead. But it is possible to do it on a purely software level or with help from hardware. So the right answer to this is both software and hardware. Any doubts on this? If not, let's go to the next question. So, which are the two kinds of semaphores in an operating system? And you have these four options. Again, a very straightforward question. Any answers to this? Okay, C, mutex and counting. Anyone else? Anyone else? Does everyone agree with C? B, binary and counting. Great. Anyone else? Let's look at the answer then. It is binary and counting, and this one is a simple matter of terminology, right? So when we talk about semaphores, we refer to them as counting and binary, depending on what values they can take. So when we talk about counting, it is simply integer values, whereas when we talk about binary, it can simply be 0 or 1, as the name suggests, and a binary semaphore is same as a mutex lock. But when we talk about semaphores, we tend to refer to them as a binary semaphore and not as a mutex semaphore. So that's the answer to this question, but it's pretty straightforward, right? So you can think about where you would use binary semaphores and where you would use counting semaphores, and what are interesting examples of both of these. And yeah, any doubts on this? I think this week is a lot more heavy on theoretical questions rather than problems that you needed to solve the way you had in your CPU scheduling. So yeah, most of them are pretty straightforward as from what I can see. Any doubts on this? If not, let's move to the next question. What are spin locks? CPU cycles wasting locks over critical sections of programs, locks that avoid time wastage in context switch, locks that work better on multiprocessor systems, all of the mentioned. This is probably not so straightforward. Think about it, I'll give you a whole minute. Any answers? Anyone? Or does this seem too confusing? Okay, let's look at the answer. So it is D, all of the mentioned, but we'll spend some time thinking about each of these options and why they are true, right? So let's first look at a mutex lock, and we have these two primitives, acquire and release, and the assumption is that they are atomic. And how are they usually atomic? Because you have hardware supported atomic instructions which make this possible, right? So the way you use this is you acquire the lock and you execute the critical section, you release the lock, and then whatever is the part of the program that is not critical, you execute that. For that you don't need a lock, right? Now this spin lock is something where when you call this acquire lock, it is going to do what is called a busy waiting. Now what does that mean, right? You can do two things when we call this acquire lock. One thing is this process can go from the running state to the waiting state where it is blocked on this event and something else can run. What happens in that case? Your CPU is not wasted, right? Because something else is running instead of this program, and the moment that lock becomes available, this process can come back and get it, right? In that case, the CPU will not be idle, but you could have another approach where you keep checking. This acquire lock will keep polling that lock variable to see if you've acquired it, right? That is termed a busy wait because you're just idling away till you get the lock. You are not doing any useful work. You're simply going and checking if I can get the lock, can I get the lock, can I get the lock, can I get the lock, and you do this for a lot of time, right? So this, the name itself, spin lock, refers to the fact that you're spinning in this loop in where you're not doing anything useful because you're simply checking this over and over again. And that's also called a busy waiting, where the CPU is kept busy but all it is doing is actually waiting for this lock, right? So that is about the option A, where the CPU cycles are actually wasted in trying to get this lock for a critical section. Now let's talk about the context switch part. Now in the first option that I discussed, where you have a process and then it goes to the waiting or the blocked state, then what you need to do is you need to do a context switch. You do a switch out of this process, you switch in something, and then when the lock can actually be acquired, you switch out whatever is currently running and switch this process back, right? So that requires 4 context switches, and context switches are typically expensive. Whereas think about the spin lock approach. So you're constantly checking, can I get the lock, can I get the lock? So you're not switched out, there is no context switch happening. Now so think about both of these approaches and when each of them would be beneficial. So if we talk about a spin lock where there is no context switch but instead a busy wait, it could be very useful when the lock is expected to be held for a short time. For instance, imagine that you have to wait, let's say 10 milliseconds to get this lock, right? And instead of a busy waiting, you went for a blocking kind of an approach, right? Where your process is put to sleep or it's made to wait. Now this context switching itself might take, let's say 1 milliseconds. So you spend 1 millisecond switching it out, then something else runs, and then you spend 1 millisecond again switching this new process in, and then once the lock is available, you switch out this new process and you switch back your waiting process, right? You've spent 4 milliseconds context switching and just 6 milliseconds running something else, and then you get the lock, right? That is maybe not such a good example for a spin lock because this context switch overhead is very high. So that's talking about this. But in case you were expected to wait, let's say 2 milliseconds, instead of doing this whole context switch, what you could do is simply hold the lock and spin. Keep checking, and within a short amount of time, you actually acquire the lock. So you avoid the context switch overhead, and it's okay if you do this busy waiting, that is wasting CPU cycles, because it is for a short time. Whereas if you are expected to wait a long time, a better approach would be that you switch this process out, bring back something else that can execute while this is waiting, right? So that's about the option B. Spin locks are locks that avoid wastage in context switches. So when you decide to use a spin lock versus something that doesn't do a busy wait depends on how long you're expected to wait for that lock. Now let's talk about the third example, right? Again, this is beneficial in multiprocessor systems because you can have one thread that runs on one processor or maybe even one core, and that can just spin or keep doing this busy wait while another thread performs its critical section on another processor, right? Whereas if you have a single processor or a single core kind of environment, if you have one thread that is actually doing this busy wait, the other thread cannot run because this thread is taking the processor, and the other one will simply have to wait till this is switched out. So it's bad because you're not doing anything using this thread, and the other thread that can actually do work is just kept waiting. Whereas if you have a multiprocessor system, you can afford to do this waiting idly on one processor, whereas on another processor, the thread that can actually have work in the critical section can execute, and therefore they are said to be locks that work better on multiprocessor systems. So this makes the right answer, all of the mentioned, and hope this is clear. I don't think this was covered in detail in the lectures. So hope this explanation helped you understand. I'll wait a minute for you to take in this information and ask questions if you have any. Great, no doubts. Anyone else? Great, no doubts. So we have about 15 minutes left. So I'll again ask if anyone has doubts from the week 7 course contents, please post it on chat. I will take up those questions or doubts towards the end of the session once we are done with questions, but please feel free to ask. These sessions are meant for you to get your doubts clarified. Okay, let's move to the next question. The bounded buffer problem is also known as producer-consumer problem, reader-writer problem, dining philosopher's problem, none. Any answers to this? C, dining philosopher's problem. Okay. Anyone else? A, producer consumer problem. A. Okay. Anyone else? Okay. So the right answer is A, producer consumer problem, and it's just a question that tests your understanding of the terminology, right? So in the producer consumer problem, the problem probably wouldn't be as bad if you had an infinite buffer, right? You just could keep on writing because there's no limit, and you didn't have to do as much synchronization. But because you have this buffer which is of a finite size, you actually have to do all of these things to make sure that it still has space to make sure that the producer is not writing too much before the consumer has consumed and all of that stuff. So that's why the producer consumer problem is also referred to the bounded buffer. But notice the different aspects in these three variants. That's what comes to my mind when I see these options. For instance, the readers writers problem has this interesting concept of what do you prioritize when there are multiple readers and multiple writers. So that's symbolic of doing reads and writes. So can you have multiple reads together, and can you have multiple writes together, and can you have a read and a write together? So that sort of thing is what is unique about the readers writers problem. Whereas when you think about the producer consumer problem, it's a simple thing of having one, maybe you can think of it as one reader, one writer kind of thing, and different entries in the buffer, right? So these are slightly different from each other, and looking at what's different between them will tell you how many versions of these synchronization problems are actually there. That's why these classical examples are put forth, right? Because they are representative of a large number of real world problems. But this answer to this question, I think, is pretty straightforward. So I will move on in the interest of time. So how can priority inversion be solved? Special atomic instructions, busy waiting, priority inheritance, none of the above. Any answers to this? Anyone? Do you remember what is priority inversion? Okay, if not, okay, I see. Someone says busy waiting. Great. After this lecture, I don't think you'll forget what's priority inversion. I have a nice case study that will probably, at least for me, it was that way. I never forgot priority inversion after this. So let's first start with a recap from the previous week's lecture. So the answer to this is priority inheritance, but let's first recap on what is priority inversion, right? So we spoke about all of these things like deadlocks and starvation, which are basically things that you don't want to happen, right? Deadlocks happen when two or more processes are waiting for an event that can be caused only by one of the waiting processes. So it's very simple to give an example of this, where you have one process does a wait on S and then a wait on Q, and you have the other process doing the exact opposite, right? So say this has executed wait on S, and then this executes, and this does a wait on Q, and after that this one executes, and it's going to be blocked here forever, because it's kind of a cross dependency, right? This one has what this wants and this has what this wants, and they'll never come out of this. This is called deadlock. There's a slightly different variant of this called live lock. Maybe we'll see it in a later lecture. Similarly, something that you don't want happening is starvation or an indefinite blocking, where a process keeps on waiting to get access to a shared variable and it never does, right? That indefinite blocking is referred to as starvation. Now, what is priority inversion? It's a scheduling problem where a lower priority process holds a lock needed by the higher priority process. And what happens when a lower priority process holds a lock needed by the higher priority process? Because there is this notion of priority based scheduling, the lower priority process that's actually holding this lock might get switched out, and the scheduler might choose to execute the higher priority process. The higher priority process actually needs this lock which is held by the lower priority process, so it also can't execute. And this might keep happening, and the lower priority process never gets to execute, so the higher priority process never gets this lock. And as a result, even though this process has higher priority, it essentially becomes, its priority essentially becomes lower than this lower priority process because of this phenomenon. This is called priority inversion, and this is solved by priority inheritance protocol, which basically means that the the priority of the lower priority process is temporarily boosted up so that it can quickly finish up its critical section and return the lock, so that thereafter the higher priority process can actually execute. And this might still be very abstract at this point, so we look at a nice case study for this. So yeah, here's one, right? So the Mars rover with this Pathfinder, which was launched somewhere in the 90s, 97 or something like that. This is about that, right? So if you're thinking all these OS concepts are completely irrelevant and they never play a role in real life situations, here's something to change your worldview. So here are some facts about how the Mars Pathfinder was built and developed. So one thing that stands out to me is, instead of a 10-year schedule, it was built in less than 3 years. And yeah, that's some stuff about the Pathfinder. You can find more if you look it up. But what happened to this is, within a few days of landing, the spacecraft began experiencing total system resets, as in a reboot. And it's bad enough when a reboot happens as an end user with a laptop, right? Because saying, oh, I was working on this and I lost everything. If it happens in a spacecraft that people spend millions of dollars sending into space, it's really bad, because software that goes on a spacecraft has to be perfect, right? Because you lose data that you collect during each cycle, and it's really expensive to do this, so you don't want that happening. So let's see how this was debugged and what they found. So obviously they have an exact replica of the spacecraft in a lab situation. That's precisely to debug these things, because you can't actually go and turn on debug logs in a spacecraft, because you would have very limited space to store these logs on, and it would hamper the performance of the system. So anything that you do would have to be done on a redundant replica that you're not actually using. So the OS that was used here was VxWorks, and the tracing feature was completely turned on. So this would mean that you have huge amounts of logs, right? You get all system events like context switches, synchronizations, interrupts, and things like that. And like I said, the tracing is disabled on the actual spacecraft because there's too much data and you can't have that happen. So this is a very, like, an optimal kind of design requirement is there when you send a spacecraft out, because you can't have too much data, you can't have it use too much power, you can't, lots of constraints like that, right? It has to operate in a certain temperature, it can't have these system resets and things like that. And this problem was kind of debugged in a few days, and it was found to be a result of priority inversion. So there was one high priority task called something, and this was actually taking a little longer to complete its work. And why? It was waiting for a shared resource that was held by a lower priority task, but the lower priority task kept getting preempted by multiple medium priority tasks, because the scheduler thinks, hey, this is a low priority task and there's a medium priority task waiting, so let me just preempt this one and run the medium priority ones. So now the medium priority ones run, and then whenever this high priority run is scheduled, it's just going to wait for this shared resource that is trying to get, and it never gets that resource, and ultimately there is some scheduler in the system that tries to check for these kind of situations, and it thinks, okay, something's wrong with the system, let me do a full reset. So it keeps performing this reset, and this kept happening. So this is how it was, ultimately it was fixed by a simple priority inheritance, right? But the problem and the scale at which it manifests, when you spend $150 million sending a spacecraft out into space, if something like this happens, it's close to catastrophic. So that's priority inversion for you, and that's how it manifests, right? So I hope this is clear now and you understand what priority inversion and the solution to it, priority inheritance, which is basically that you boost up the priority temporarily so that it gets to execute and release the lock. Any doubts on this? No doubts? Great. I'll just wait for 10-15 more seconds in case anyone else has any questions. Okay. I think this is the last question I had for today. But I have one of these things that I meant to do in a previous session and that I hadn't, so I put this in. So throughout scheduling we spoke about throughput, right? And in our earlier classes, things very early on in the course where we spoke about architecture and we said the access latency of a disk or the access latency of memory. So latency and throughput might initially be a little confusing. So I'm hoping this helps you understand it better. So latency is the execution time or the time taken to finish a task, whereas throughput is the number of tasks that you can finish in a fixed time, right? And when you exploit parallelism, you don't change latency, you change throughput, right? Because you're doing 5 things in parallel now. So what that means is that you can get more of these done per unit time. But the time taken to finish a single task does not change. That is latency, right? Now let's take a very simple example for this, right? So suppose your goal is to move people by 10 miles, right? You're transporting people for 10 miles. Now let's take the example of a car which can seat 5 people and its speed is 60 miles per hour. Whereas let's take a bus where the capacity is 60 people, whereas the speed is much slower, it's 20 miles per hour. Now latency of the car is 10 minutes. So you need to move 10 miles, this moves 60 miles per hour, meaning it can move 10 miles in 10 minutes. Whereas this is 3 times slower, so you take 3 times longer, right? So the bus takes 30 minutes. So this is latency. This is how much time it takes for you to go from place A to place B when you're in a car versus when you're in a bus. Now if we talk about throughput, it's how many people a car is transporting per hour, which is 15, right? Whereas if you talk about a bus, it is 60 people because a car takes 10 minutes and it transfers 5 people. Okay, so here you're counting the return trip. So I'm sure you guys can work out this math and come up with this number 15. But this is the difference. This is the throughput. So how many people are you transporting? And in a bus that comes out to be 60. So if you use latency to compare a car and a bus, the latency of the car is lower and a lower latency is better. But if you're trying to compare throughput, then the throughput of the bus is obviously higher because it can transport more people, right? So these are 2 different metrics and you use them in different places. For instance, for a web server, you might care a lot about throughput. How many people can you handle at the same time? Whereas if you have a program that's maybe trying to predict weather, you care about how long it will take to finish, right? The latency. So you choose this metric depending on your goals. And I think you have a little more of a comparison on the right side, which I won't go through, but it's for your reference, and you can also refer to the slide credits to get a more detailed slide on this. So I think we're almost at time. So this is pretty much everything I had. Any questions, any doubts that you have? If you have no doubts, thank you for showing up to this session. I hope you learned something useful from it, and I look forward to seeing you guys next week. And thank you so much for making it an interactive session. And I'll stay on the call for 1 more minute. In case you have questions, please feel free to ask. Okay, if there are no questions, thank you so much. See you next week.